In this lecture, we're going to be looking at the equations of motion for our basic performance estimates for aircraft design. So one of the things that we'll need to do if we're looking at estimating how well our aircraft performs any particular mission, we had to be able to calculate lots of design parameters as part of that analysis. To do that, we had to figure out what those equations of motion look like first. So let's benchmark, go back to our first case study, performance analysis of the Wright Flyer. Don't have a lot of data about how well this aircraft actually performed on its first flight, other than its flight only lasted 12 seconds and only covered 120 feet. Now, even with these rudimentary numbers, however, we can at least determine what the average velocity was over that flight time, and then go back and look at some of the design parameters of that aircraft. For example, the weight of the aircraft, the wing area, the wingspan, some drag estimates, to be able to determine some more details about the overall aircraft performance. Now, if we take this into the modern era, what we're interested in is calculating something like this. For an F-22, how long does it take to take off? How long does your runway need to be? What's your stall velocity? If you're going to perform a pull-up maneuver and a vertical flight, what would your aircraft be able to do under a certain set of design parameters? How fast can it fly? How quickly can it execute that pull-up maneuver? How long, to what altitude could you fly vertically? So if you have enough information about the aircraft and you have design equations to go along with that, you're able to calculate all of these values. Now, all this kind of goes back to some of the questions we've asked earlier in the semester. If you want to build, the next best aircraft, you have to ask yourselves some very basic questions. First is, how do you know it's the best design? Other than going out and building your aircraft and comparing the performance of those prototypes, what ways do you have to compare one aircraft against another? So in this case, you want to be able to have a set of equations that allow you to look at different performance estimates of those aircraft. In this case, that will then allow us to evaluate different design options. Rather than just comparing, say, aircraft A versus aircraft B, you can also look at different design options as part of your trade study analysis. So far, we've looked at these fairly qualitatively. What we want to be able to do now is to do a quantitative analysis when we're evaluating different design options as part of your trade study process. Then this lets us compare different designs. So now you have a panoply of different designs that you've used for your aircraft, so you can compare something like a traditional aircraft design with a blended wing body with a strut-braced wing design. So obviously you may not have a lot of benchmark data you can work with really any of these aircraft designs that we're showing here. So if you have a set of equations that are reliable enough, it now allows you the ability to compare all of these designs against one another. Not only comparing apples versus oranges, but, different apples with each other. So, when we come back and look at performance, we want to answer the basic question, how well does the aircraft perform? And when we say perform, we mean lots of different things. Some of these are going to be analyzed using a level and steady performance calculation when we're looking at the aircraft essentially in cruise flight. So it's level, not increasing altitude, not ascending, and not decreasing altitude, not descending, but also steady. The aircraft is not accelerating. It's flying at a constant velocity. And that's where the aircraft is going to be spending most of its time. In a traditional airliner role, the aircraft may spend 90 to 95% of its time within that cruise flight mode, essentially in level and steady flight. And from that, we can ask ourselves some basic questions. Do you have enough thrust? Do you have enough power? And then you can determine some very simple performance estimates, such as how fast can it go? How slow can you go? How fast can you fly? Or how fast can you climb or descend? What is your range? What is your endurance? When we start to take a look at unsteady flight performance then, it allows us to answer a number of different questions where the aircraft is essentially changing not only its attitude but also its velocity. How long of a runway do you need to take off? How long of a runway do you need to land? Are those two values close to one another? How tight of a turn radius is your aircraft going to have? How fast does it turn? What is that turn rate? What does your pull up or pull down maneuver look like? How quickly can the aircraft accelerate? So when you start applying unsteady loads to your aircraft, where the sum of your forces are no longer equal to zero, if we have these equations, they allow us to calculate a number of other different performance parameters. And so we're going to end up with a whole range of different values that we're going to calculate throughout the semester, and you're going to be calculating each one of these for your particular aircraft design. Now, one of these we already know how to do, stall velocity, for example. So you know how to calculate that. As long as you know some basic performance parameters such as wing loading, the altitude you're going to be flying at, and the stall lift coefficient, you can calculate the stall velocity for your aircraft. All these others, we need more information before we can go through the process to be able to calculate those values. Now, some of these are going to be functions of the payload and fuel of the aircraft. For example, you know that since the stall velocity is a function of the wing loading, assuming you aren't changing the wing area of the aircraft, when you're burning fuel throughout flight, your stall velocity is going to change as well. So the stall velocity that you start off with at the beginning of your mission is going to be different from the stall velocity at the end of your mission. Many of our performance parameters are going to be functions of the weight of the aircraft, and so they're going to be also then functions of where you're at within that particular timeline of your aircraft operations. Now, some of these parameters we're going to calculate can be determined by a single number or a set of numbers based upon your payload and fuel. Others are going to have to be determined graphically. And so we'll also develop a number of different performance plots as part of this, so we can look at the range of values that we'll see. For example, thrust required and thrust available, power required and power available as a function of velocity. We already know how to calculate the power and thrust required for our aircraft as a function of velocity, and we know that there are going to be minimum values for each one of those and a velocity associated with each one of those values. So while those values will be determined by a single number, we'll need a range of values since we know that they increase on both sides of that minimum range. So the same is going to be true for rate of climb, time to climb, our payload range and our payload endurance diagrams, our load factors, flight envelope, and etc. Now, some of these are going to be important for aircraft performance analysis. Others are going to be critical for aircraft operations. For example, your CG travel is an important parameter that pilots need to calculate before any mission. So as your payload is loaded on the aircraft, the pilots will need to calculate based upon the amount of payload you have and the location of that payload on the aircraft, as well as the amount of fuel that you have to determine if your center of gravity is within the right range. If your center of gravity is too far forward or too far aft, your aircraft may become unstable. So that becomes a very, very critical value that pilots will need to be able to calculate. Now, we can look at a lot of these values across a range, or kind of a roadmap of what's going to happen with any particular aircraft flight operation as it goes through the process of taking off, climbing, cruising, going throughout a mission. In this case, we have a fighter aircraft, through turning flight, landing, and then coming back, and then its mission ends when it returns to base. So we'll use both our level and steady and our unsteady performance calculations to be able to essentially predict how well this aircraft is going to perform in terms of its altitude as a function of time, airspeed as a function of time, and then weight in terms of how much fuel is required to perform each one of these phases of its mission. So at the end of this, we should be able to generate a plot like this for our particular aircraft, regardless of that aircraft's mission. Now, we already know that we have a number of design parameters that we can use as part of this analysis. So as long as we know what these values are, it doesn't really matter what our aircraft looks like. so we can essentially determine the performance of the aircraft based upon some singular design parameters. Wing loading, lift to drag ratio, thrust to weight ratio, and power to weight ratio are going to be the most important of these. Now, most of these will have some kind of functional relationship. So for example, where we're at on the drag polar is going to make a big determination of how well our aircraft is actually performing. So as we move around from point to point on that drag polar, it's obviously going to change how well our aircraft performs at any given flight phase of our particular mission. Now, as we mentioned, we can kind of break these up into two groups: steady flight performance and accelerating or unsteady flight performance. So we're going to look at each one of these in turn. So our basic equations of motion, there's nothing new here, so we're using equations of motion that we've already developed in other courses, but primarily we're going to be looking at the balance of the forces that are going to vary depending upon both the attitude of the aircraft, what orientation is the aircraft in, and then whether the aircraft is accelerating or not. Now, keep in mind that when we say acceleration of the aircraft, it's not just whether we're changing the magnitude of the velocity, but it's also whether we're changing the direction of the velocity. And that is going to indicate that our aircraft might not only be accelerating, changing velocity, but it could also be in turning flight. So our aircraft could be in a banking maneuver or a pull-up, pull-down maneuver, and that would still be unsteady flight even if we're not changing velocity. Now, in order for us to examine the forces on the aircraft, we need to make several overarching assumptions. First, our forces are always going to act near the center of gravity of the aircraft, and we're going to define this by our aerodynamic center. So we're really not going to look at asymmetric forces acting on an aircraft. We're going to save that for another course and really look at the impact of that on stability and control in the future. So we're looking at bulk forces acting on our aircraft. Second, all of our motions are going to be governed by Newton's second law. So that's obviously going to be true since our aircraft are traveling well below the speed of light. However, the mass of the aircraft may change during flight, and this is important. Even if we have an electric aircraft where we're not burning any fuel, we may be changing our payload. But for all of our aircraft that are operating off of hydrocarbon fuel, our weight will change since we're burning fuel within flight. Now, it is important that even though our mass of our aircraft varies, this is going to be on relatively long time scales compared to the velocity of our aircraft. So as we'll see in later analyses, when we look at flight of rockets, for example, those masses vary on relatively short time scales, and those are where you're getting most of your thrust from, based on the fact that you're burning lots of fuel in very short periods of time. For aircraft, we're taking a lot of fuel, but we're burning it over long periods of time. But it is important that we're using the assumption that the mass of the aircraft is going to change. And that's going to be very important when we start looking at things such as range and endurance. Now, first, in level and steady flight, our basic flight analysis and our free body diagram is going to look something like this, where we have lift balancing weight and thrust balancing drag for a given velocity. Now, one thing that we'll throw in here just to start off with, to mix things up a bit, is our thrust is not always going to necessarily be aligned anti-parallel to the direction of flight. Our drag will always be acting within the direction of flight of the aircraft, or the direction of the velocity vector of the aircraft, and then our lift is going to be perpendicular to that. As we'll see later, when we start looking at unsteady flight and our aircraft is climbing, the relationship may change. Now, the reason that we're looking at our thrust line, which may be offline, that velocity vector, is because as we change the attitude or velocity of our aircraft, we know that we're going to be changing the angle of attack. Obviously, for most aircraft designs, the orientation or how those engines are mounted on the aircraft are not going to change. So there is some expectation that you're going to have your thrust vector slightly offline, and typically that's going to be slightly up, so that's going to essentially counteract the impact of the weight of the aircraft. Now that angle may be small, so it's usually a good assumption. You can assume that epsilon is going to be equal or close to 0, but it's always, good to make sure that you carry that forward as well. Now, it's worth noting here the difference between airspeed and ground speed of the aircraft. We haven't talked a lot about velocity, so we'll come back and discuss that later in terms of things such as true airspeed and indicated airspeed. For now, it's enough to know that for our aircraft, all it really cares about is the airspeed, and that's the value that we're going to be using for our V infinity. That airspeed may not be indicative of the ground speed of the aircraft, and that's going to be important when we're calculating things such as, time to go from point A to point B. So it's important to look at the wind and how the velocity of the aircraft compared to the ground speed of the aircraft may be altered by changing the relative wind of the aircraft. Very simple example of this would be your aircraft has a speed of 500 knots. Your wind is moving with a 100-knot headwind. That means it's coming towards you, so thus your ground speed is going to be equal to 400 knots. So that's going to be the velocity that an observer would see you traveling as they're observing you from the ground. So you could look at these in a number of very simple cases. If your wind is 0, obviously your airspeed and ground speed are going to be the same. If you have a 100-knot tailwind, that means your airspeed is still going to be 500 knots, but now your ground speed is going to be 600 knots. That would be the velocity that an observer sees you on the ground. So if you had a headwind that was equal to your airspeed, your ground speed would be equal to 0. As far as your aircraft is concerned, however, it doesn't notice that. All it cares about is the airspeed of the aircraft. So everything we're going to be calculating is relative towards that airspeed. But when we're trying to calculate things such as, time it's going to take to go from point A to point B, it's important to consider that, that headwind and tailwind velocities. Now, when we're looking at headwinds and tailwinds that may not be directly aligned with the velocity or direction that our aircraft is traveling, then obviously things such as our heading is going to change as well. And this is important primarily from a navigational perspective. So if you're trying to travel from point A to point B, but you have a wind that's going to be pushing you in one direction or the other, that's going to change not only your ground speed, but also the direction in which you're traveling. Now, for our cases, we're not going to really be looking at this in too much detail, but it's important to understand at least where this is coming from. Now, in level and steady flight, first thing we're going to do is look at the forces that are perpendicular to the aircraft. And again, we're assuming that it's level and steady flight, so that means the sum of our forces are going to be equal to 0. So in this case, we have lift minus weight, plus we have a little bit of thrust as well, due to having that thrust line slightly inclined against the direction of velocity of our aircraft. So that gives us then a lift is equal to weight minus thrust times sine of that angle of the thrust line. Now in the case where that's equal to 0, this simply is reduced to lift is equal to weight, what we've already seen. Likewise, for the forces parallel to the direction of flight of your aircraft, again, those are also going to be equal to 0. Then we have t cosine of that angle minus the drag of the aircraft. So thus you have drag is equal to thrust times the cosine of your thrust line. Those are our basic equations that we have in level and steady flight. That's it. That's as hard as it gets. Now, let's make this a little more interesting and look at climbing flight. Now, first thing, when we say climbing flight, we're going to be changing the altitude of our aircraft. We can either be ascending or descending. It doesn't matter. But it's important to note that we're going to be still in steady flight. So we can consider this steady but unlevel. So we're not accelerating, we're just changing our altitude. And what that essentially requires us to do, since we're changing the energy level of our altitude, or energy level of our aircraft, I should say, we're going from one energy level to another energy level, that's going to require extra energy put into our aircraft, or we're going to gain extra energy if we're actually descending. So in this case, now all of our forces are not aligned. You'll notice the weight of the aircraft is always pointing towards the center of the Earth, but now we have a climb angle associated with the aircraft, where that aircraft is inclined at some angle as it's increasing its altitude, as shown in this particular case. Drag, again, is always going to be parallel with that velocity vector, and lift is always going to be perpendicular to that velocity vector. But now we have both a component of the weight and the thrust within that line. So as we develop our equations, we end up with one extra term in each one of those, primarily that weight times cosine of theta term within that lift equation. So we've just modified that by having a cosine of theta, but now we also have a weight term within our drag equation. So drag is equal to t times the cosine of epsilon, or that thrust line, minus weight times the sine of theta, where in all these cases theta is our climbing angle. Now when we go to climbing accelerating flight, in this case we're not only changing our altitude, but we're also inclined in a pull-up or pull-down type of maneuver. Now we're starting to introduce centrifugal forces on the aircraft. So in this case we have essentially a curvilinear motion that the aircraft is traveling on. So you can think of this similar to that pull-up maneuver that we saw the F-22 perform earlier. So in this case, at any particular point in the aircraft's motion, we can assume that that aircraft is turning along a very large circle. So we'll have a radius of curvature associated with that. So we'll be looking at this at an instantaneous point within the flight mode. So in this case, we'll now use those unsteady equations of motion, again going back to Newton's second law, where we have F is equal to ma. Now for the forces parallel to the direction of motion, that simply becomes m times a, where a is now your dv dt. That's the rate at which you're accelerating along that particular direction that you're traveling at any given point in time. Now your forces perpendicular to flight, however, are going to be given by your centripetal equation, where you have F is equal to m times the acceleration perpendicular to your velocity vector, which in this case is going to be m times v squared over r, where r now is that radius of curvature. So you can use this for any instantaneous portion of your flight, and that will tell you then what those forces are acting on your aircraft. Now, when you combine all these together then with the previous equations that we derived, we now can come up with a full set of equations for our aircraft at any point in time. So our aircraft is now climbing, it's changing its altitude, as well as accelerating, it's changing its velocity vector. So in this case, we'll have mv squared over r, where r is now, in this case, our pull-up radius, is going to be equal to the lift that we're generating plus t sine times sine of epsilon minus weight times cosine of theta, where theta is our climb angle. And for the forces perpendicular to flight, we'll have m times a, which in this case is dv dt, is going to be equal to thrust times cosine of epsilon minus d minus weight sine of theta. Now, this is a very simple but accurate set of equations for the basic assumptions that we set at the beginning of this analysis. So this is going to be enough for us to be able to kind of predict how that motion of the aircraft is going to behave within a fairly limited set of assumptions. At least enough for us to go through this very basic performance analysis. Now, for the most part, we're not going to see this form of the equations again until we come back and look at takeoff and landing of an aircraft, where in that case we're going to be accelerating, but not really changing our radius of curvature when we're on the runway. Then when we start to perform that transition and climb out, then we'll transition from the parallel equation to the perpendicular equation to determine what that radius of pull-out is going to be. And then we transition back into a climbing flight equation. Until then, however, we're going to be using the previous set of equations where we're looking at both level and steady flight and then climbing and steady flight. Now, this is only looking along the direction of motion of the aircraft. If we want to bank the aircraft, now we'll have to look at the aircraft from a slightly different perspective. In this case, when we start to bank the aircraft, what we're doing is we're generating a lift force along a direction of turn for that aircraft. So in this case, we're going to bank the aircraft, and we're assuming that our lift is going to increase. So in this case, we're increasing the angle of attack, so we're still able to maintain a level flight altitude. So we're essentially performing a coordinated turn for our aircraft, so where we have a radius of curvature associated with this turn, but we're no longer ascending or descending within our particular motion of flight. Now, we will also have a portion of our thrust acting along this aircraft. This is usually going to be pretty small, so for the sake of this analysis right now, we're going to ignore that and just really focus on the basic lift and weight balance of the aircraft. So now we have associated with this a bank angle for the aircraft. So in order to maintain altitude, the lift that we're generating off our wing that's acting in the vertical direction, or lift times cosine of phi, has to be equal to the weight of our aircraft. If that's not true, then we're either going to increase our altitude if that left side of the equation is greater than weight, or we're going to decrease altitude if that left-hand side of the equation is lower than our weight. Also, to maintain this banking turn, it also must be true that the forces acting along our horizontal axis must also be balanced. So in this case, lift acting in the horizontal direction, or lift times sine of that bank angle, has to be equal to your centrifugal forces, m times velocity squared over the radius of that bank. So if you know what your velocity is, the weight of your aircraft, then you can determine your mass. Given your lift and your bank angle, you're going to be able to determine what that bank radius is going to be. Now, this requires a little bit more detail because really what we're going to be doing when we do this control is we have to put our aircraft within a bank itself. And this is going to introduce a number of different things. First, since the lift of our aircraft is no longer equal to the weight, when our banking turn, we're going to be generating more lift than the weight of our aircraft. And this is really going to determine the structural design of our aircraft. How much load is our aircraft actually able to take? And this is going to be very important for the structural analysis portion of our aircraft phase. So we'll come back and look at this when we look at VN diagrams, where N is now our load factor and is defined by our lift divided by the weight of our aircraft. That's going to determine how much of a bank we can actually make with any given aircraft design. It's also going to determine what we can do in a pull-up and pull-down maneuver. Now, to also do this, we have to have some control surfaces being deflected on our aircraft. So if we want to have a coordinated turn, then we're going to have to be able to look at how those different controlled surfaces are interacting with the overall motion of our aircraft. So we'll also come back and look at that as well. And that's going to change the balance of forces that we're going to see acting on this particular aircraft. Now, what that gives us a very simple, overly simplistic, but enough for our analysis, set of equations of motion. So now we have equations that are acting along the flight path, equations acting along that flight path but within the vertical direction, so our pull-up and pull-down maneuvers, and then equations of motion for a banking turn of the aircraft. And this is simple enough for you to be able to generate a very basic flight simulator. You won't be able to do things such as, predict whether your aircraft is going to spin or not, but it's going to be enough that you can do some very basic performance analysis of your aircraft along any given arbitrary flight path. Now, very simplistic, but let's look at some of the limitations. First off, we did ignore side forces, as we mentioned. So we're not going to be able to see what's going to happen on our aircraft, for example, in yaw. I can't really tell if our aircraft is going to be stable or unstable, these equations. So we'll have to come back and look at that later when we examine stability and control, and that's really going to be important in determining things such as tail sizing and control surface deflections. Also, we assume that the curvature of the Earth has no impact, so the weight always acts down. Now, since the plane is going to be flying level and steady, or at least level with the ground, that assumption is okay. If we're looking at a very large aircraft or a very small Earth, then obviously that assumption, doesn't really hold water anymore. Also, we have not examined forces acting at different points on the aircraft, such as lifting surfaces, and maybe lift from a tail or lift from a canard. So in this case, you're not going to be able, as you deflect those control surfaces, to be able to examine how that's going to change the attitude of the aircraft. Also, we ignored the inertial mass of the aircraft, namely as you're changing your velocity, accelerating, decelerating, how that's going to behave, particularly in things such as a banking maneuver. An aircraft that's going to have a lot of mass on its wingtips is obviously going to behave very differently than an aircraft that's going to have its mass all towards the center of that aircraft. And also, we've only looked at translational and instantaneous motion only on the aircraft. So there are a lot of limiting factors here. That's okay. We'll come back and suss out all these details at a later date. With this, however, it does allow us to look at some very simple motion of the aircraft. So you'll have one MATLAB code which provides, based upon these very simplistic equations of motion, for our point mass. We can look at the longitudinal behavior for the aircraft and determine things such as an equilibrium flight path, or non-equilibrium in this case, where we can look at how that aircraft is going to behave giving a certain velocity. So you'll be doing this on your initial homework. So in this case, using these equations, you can look at a resulting state vector, which is going to be a set of ordinary differential equations that you can then solve relatively easily. Now, another thing we need to come back and talk about is the impact of the design choices that you make on your aircraft. That's going to have a very, very large impact on what your overall performance is going to look like. Going back to our previous discussion where we have power required for your aircraft, the amount of power that you have available is going to be determined by your choice of power plant or propulsion system that you have on your aircraft. Thus, using a shaft-driven propeller versus selecting a gas turbine for your aircraft is going to result in very different overall performance behavior. So you have to keep that in mind as you're going through this overall process. One of the aircraft that we're going to be looking in stark detail for this next phase is the F-16. So given design parameters of the F-16, things such as wing loading, aspect ratio, zero lift drag coefficient, can we then predict the performance of this very fine aircraft?